Any question, guys? If you don't ask question, you will not learn much, right? You can learn better by asking questions, by asking critical questions, by asking hard questions, tough questions. If you don't ask questions, you will not get much insight of the subject. Because I don't know what part you have understood and what part you didn't understand. Okay, so now today first we'll proceed with a little first start with a small modification of this circuit. We'll add a resistance here for what this circuit we have. So you see if we add a resistance at this point, right? Let's say we have a resistance here R. So how the different expressions will modify. Okay, let's take a fresh page, right? It will be easy to do here, but a little bit clumsy. Better take a fresh page. Next. Okay, so that is our the same the common collector, common emitter, cascade amplifier. but just we added one resistance at the emitter. So it will not be much different overall the circuit, the performance, but we'll see the how do we analyze this circuit when you have the emitter resistance. So you start with the Ri. So what will be the input resistance in this case?
Sir, R pi 1 plus Re into beta plus 1.
R pi 1 plus.
Re into beta plus 1.
So just Re, or you should have something.
Sir, Re parallel R pi 2.
Right. So this is connected to the input of Q2. So the resistance looking into the base of Q2, that is R pi 2. So that will be in parallel with Re. Right. So we will have Re in parallel with R pi 2. So that is how it will modify the input resistance. The output resistance, what will be the output resistance?
Same R not 2.
Right. There is no change in the output resistance, remains same. Okay, now we try to determine the, first start with the voltage gain. Gain we express as the product of three gains. Okay, so we assign the voltages. So at this point, voltage at the base of Q2 is our VB2. Voltage at the base here of Q1 is VB1. Okay. So what will be these voltages? Let's write it here. Okay, it's crowded. So first gain expression, the VB2, sorry, that's not VB2, that is V0 by VB2. So what will be this gain expression?
Minus GM RL parallel R not 2.
You should write actually GM2. I got that in your previous circuit. GM2 means the transconductance for the second transistor. So GM2 and that multiplied by this parallel combination of R0 and RL. So there is V0 by VB2, and next we have to write the gain for the common collector, which is VB0 by VB2 by VB1. And what we can write for this?
Sir, R pi 2 parallel RL, sorry, Re divided by R pi 2 parallel Re plus Re1.
Right. So now in this case, we have these two basically coming in parallel. So if you look at the circuit, we can maybe show it like this. Okay. From this, the output side of the common collector, and that's connected to the input of the common emitter. And if you draw the what we know call the T model, so on the emitter side of this T model, it will be like this. We have RE and we have R pi 2, right? And that is our the base point of Q2 and voltage is VB2. And then here is the right, so that is our base point of Q1 and that is VB1 and resistance here is RE1, right? So now you apply the voltage division rule here. So that's the T model, and you can usually visualize also from here. So RE and R pi in parallel, and then looking into the emitter because you are on the emitter side of Q1, resistance is RE1, right? And that is the voltage VB1 here. So and voltage here is at this end is VB2, right? So usually apply the just voltage division. Don't need to draw it, and that is quite obvious from the diagram. And we write this as RE in parallel R by 2, and that is RE by 2 as RE1. So that will be the gain expression for the common collector stage. Then the input side, we have the same, that is uh, same for any amplifier, VB1 by Vs will be Ri plus R. So the overall gain expression is now we write as minus GM2 and not 2 in parallel with RL, and that multiplied by here RER by 2 and RE plus R by 2, right? Oh no, that is not the case. RE parallel with R by 2 and plus RE1. And then we'll have the input side Ri plus Rs. So that is our overall gain, which remains basically same as before. Only here in the middle term here, so we have Re coming in parallel with R by 2. Right? So only this part gets modified. Otherwise, essentially it's the same as before. Now the current gain, what will be the current gain? Current gain expressed as I naught by II. Now that we can express, break down into a number of factors. Let's see what we can do here. Okay, the current that is flowing here is collector current IC2 for Q2. So that is our base current for Q2 IB2. Then current that is flowing here, that is our emitter current for Q1, so it's I1. IE1. And then we have here I is same as IB1. So this is how we break it down, and now we have assigned the currents. Now this one here we express like this: I naught by first term is here IC2, and then we have IC2 by IB2, and then we have IB2 by IE1, and then we have IE1 by II. Okay. So that is how we can express this gain expression, current gain, into the four gain factors, right? So first on I naught is same as minus IC2. We write minus IC2 divided by IC2. Then IC2 by IB2, that is IC by IB is beta, and you can put that beta 2. IB2 by IE1. What we can write for this one? IB2 by IE1. Hello guys. What is IB2 by IE1? It's very difficult.
So can we write 1 by beta plus 1 or something like this?
1 by beta plus 1. What's that? Hmm.
So current set.
So if you look at this, the T model, the part of the T model on the emitter side of Q1, you see that we have all these in the branches. The IE1 is the current that is basically flowing through this RE1, that is IE1, and IB2 is the current that is flowing in R5. So that is our IB2. So if you look at this diagram here, so you see that this current IE1 is basically branching out, right? Splitting, it's going through these two branches, right? So then what do you write?
So
IB2 by,
division RE divided by
so apply current division rule, and it is just
R.
RE plus R by 2, right? So this current division, right? Nothing else. And IE by IE, so that is same as IB, right? IB1. And IE by IB is beta plus 1. So beta 1 plus 1. Here IC will cancel out. So whole current gain will be minus. We have beta 2, then beta 1 plus 1. And then we have RE and RE plus R pi. So that will be our overall count gain, which is basically same as before, but with this additional factor, right? Because of the emitter resistance, we have added to the Q1, so that will take away some of the current from IE1, right? So there's some reduction in the overall current. Any question, guys?
Sir, why we added RE?
RE, that depends on your application. If you want to, fix the voltage here, doesn't want it to depend much on, R pi, the value of R pi, right? More independent. So you want a certain amount of voltage here. So when you put RE, right? So most of the voltage that will appear here that will be governed by the value of RE rather than R pi, right? Or a parallel combination of it. So that depends on your design requirement. And sometimes also instead of keep this node floating, right? If you put RE here, so that will give you more stable performance because without RE, that kind of floating that point, the emitter point. Is that clear?
Yes, sir.
Yeah. Okay, so we started with the common emitter, single stage amplifier, the limitations that low input resistance that reduces the gain, and we added this common collector at the input side, improved the input resistance, improved the overall gain. What about the output side? Is it okay, or there also we can have some problem? Okay. At the output side, the gain of the that's the gain, right? For the common collector, sorry, common emitter. So that is our gain of the common emitter, V0 by VB2 from base to collector. We have GM transconductance that will depend on the collector kind IC. So you can have a high value in that you can decide how much you want GM for your amplifier. That is multiplied by this parallel combination RO2 and RL. Usually RO2 is high in most cases. So usually what we'll have that we are approximately equal to minus GM to RL. Right? Some because are not usually in the range of 100 kilo ohm, RL few kilo ohm, right? So usually much larger. So we can approximate this to be just RL and we can write on GM. So GM is kind of fixed, right? That is fixed by the collector and IC, right? And we have seen that if IC is 1 milli in our previous uh, some lectures we did this calculation that if IC is 1 milli, then the GM will be about 440 milliampere per volt. Right? So that is, so we just 1 milli we can get a quite high GM. Now the gain will depend on the value of RL. So let's say you take a value of RL equal to 10K. So your gain will be how much? Uh, Maybe I can get rid of this part when I have some space. Okay, so we have the gain for the common collector V naught by Gb2 minus GMRL, and we have GM is 40 milliampere per volt, and RL we get 10K. So we get this to be minus 400. So again, we get a gain of 400 volt per volt. So if both are high, you get a quite high gain. Now, what happens if your RL is low? Let's say you have RL just 1K, right? So then what will be your gain?
So it will be 40.
It will be just 40, from 400 to 40, right? Drastic reduction will get. Right? So imagine even a lower, even a, let's say just 100 ohm, right? So how much will be your gain?
4.
Right? 100 ohm means if you convert in kilo ohm, 0.1K, right? So that will be just 4. Right? So in this case, your gain will be 4. Okay? Imagine even a lower input resistance is 10 ohm, then
0.4.
just 0.4, right? That is, you've got almost no gain, right? 0.4. So output side, you see that gain is heavily dependent on the value of this load resistance RL. Right? Usually we assume a high value for the load resistance, but that is always not the case. In many situations, we have load is not, you cannot control the load resistance. Load is something external, whatever you connect it to, right? Like in using a microphone, right? You cannot control the resistance of the microphone. Whatever it comes from the manufacturer, whatever is inside, that is the load resistance. So you cannot change it, right? The speaker, right? Usually, speaker, is a coil, right? And coil have very, low resistance, usually in the range of ohms, few ohms. Like I have said, let's say load is 10 ohm, really around this range. So in that case, you see that gain, you can barely have any gain, right? So the gain is heavily affected by the load resistance. So there is a problem, right? If load resistance is high, then you get high gain, but you cannot control that, right? You don't have any control over that. So how you can overcome this problem?
Sir, add a series resistance with RL fixed.
Series resistance.
Yes, sir.
So how that will help? You add a series resistance uh, with your coil, right? With your speaker, you add a series resistance here. It's the RS, right? So that is the V naught, right? And the coil will get, let's say, that's the coil resistance. So coil will get only part of this voltage, a small fraction of this voltage, right? You add a series resistance of, let's say, 10K, right? To increase the resistance, increase the gain, right? but this one remains 10 ohm, right? It's 1,000 times smaller, right? So if overall voltage here you get 10 volt, right? So you get only a small fraction, right? Still you get only 10 divided by 1,000, right? So that means 0.01 volt. Right? So is that going to help?
No, sir.
It's not going to help, right? So what is the solution?
So then a parallel one.
Connect a parallel one.
So
How it will help? If you take parallel combination of these two resistors, right? Because this is much smaller, parallel remains, right, dominated by the smaller resistors. Right? So that's not going to change anything. Okay, so we go to the first slide.
sir,
Right?
a common base amplifier.
Common base.
Yes, sir.
Okay, let's see. So what we have done here,
So I added a common collector amplifier.
okay, so we added another common collector at the output side. Now we have a three-stage amplifier, common collector, common emitter, and again common collector, cascade amplifier. So now let's analyze this amplifier and see what are the changes we are going to have. So we start with the input resistance Ri. Ri will remain same as before. The input side is same as before. So it's R pi 1 times beta plus 1 that multiplied by RE in parallel with R5. The output resistance, now that will be very different. Right? What will be the output resistance now?
So RE plus R naught.
RE, okay, so looking into the, here, looking into the emitter, right? You see small RE, you see RE3, right? So that will have RE3, and that plus, then that is connected to the, that is, we come here base, and base is connected to the emitter of Q2. And if you look into the emitter of Q, sorry, the collector of Q2, you see resistance of R02, right? So now RE3 plus,
So R naught 2 by beta plus 1.
right? So R0 is the, is in the base side of Q3, and we are looking from the emitter side. So we have to apply the resistance reflection rule here, and we write that will be R02 divided by beta plus 1, in this case beta, for the third transistor beta 3 plus 1. So that will be output resistance. You see that this is the output resistance for the common collector. We know common collector has a low output resistance, so we will have a low output resistance. We are not getting much divided by beta, and RE3 is very small. And now the voltage gain. What will be the voltage gain? Right. So there are 3 transistors, and we have 4 gain expressions. V0 by VB3, then VB3 by VB1, VB2, then VB2 by VB1, VB1 by VS. 4 gain expressions altogether. Start with the first term here, V0 by VB3. So what will be this? This is the gain of the common collector, no?
Yes, sir.
It's very simple, not difficult.
Sir, RL divided by RE plus RL.
Right. So that will be RL divided by RL plus RE, RE3. So that will be the gain expression. You see that common collector has gain, almost unity gain, but that is true if RL is high. If RL in the kilo ohm range, this in ohms range, you can ignore this, or it's approximately equal to 1. But if RL is very low, in the range of few ohms, like 10 ohm, right? So this will be not, I mean, close to 1, because RE3 is also in the range of ohms, and it can be 10 ohms, 20 ohms, right? Depends on the value of the DC bias current, IE, right? So because RE is VT by IE, so it depends on the how much is your IE or IC. So that depends on this current, right? So if this current is high, this will be low, and if this is low, if for IE, if this is 1 milli, If this is 1 milli, then you get about 25 ohm, right? So in this case, it will be much smaller, right? About 1/3 or 1/4 this, so much smaller than 1. So anyway, so next our next gain factor is VB3. So the main thing is that we cannot approximate this to 1 in case we have low RL. Right? So the second factor is VB3 by VB2. And what is that VB3 by VB2? VB3 is our voltage here, and VB2 is voltage here. So that's basically the gain of the Q2, which is the common emitter. So what is the gain expression for common emitter? Yes, we have used, so we have been using this gain expression, right, since day one, and we're using this in almost all lectures, and we have used this also in these lectures, in this today's lecture also a couple of times. So what is the gain of expression for the common emitter?
So minus GM into
Right, minus GM is GM2 times what?
GM times into R not 2
And not 2, that will be in parallel
with sir RE3 plus RL.
with just that.
Sir, not
That
R3, sorry, R pi 3 plus RL.
just RL, RL in the emitter now. You are from the base side.
Oh, yes, sir.
It will be easier if you think like this.
Oh, sorry, sir. Yes. Only, yeah.
So this output of the common emitter is connected to the input of the Q3, right? So looking into the emitter, sorry, looking into the base of Q3, what is the resistance? Let's call it Ri3. So that will be kind of the load resistance for Q2, right? So for Q2, we can draw it like this. We can show it like this, that we have here. This is our Q2. This is base, voltage is VB2. And then it is connected to the Q3, the voltage is VB2. And looking into the base, it gives a resistance Ri3. So Ri3 in this case is the load, like a load resistance for Q2. Right? So the gain expression that we'll have, so R02, that will come in parallel with Ri3. So that will be our gain expression. And what is Ri3? Ri3 is R pi 3, and then that plus beta plus 1 RL, right? Now, since RL is in the emitter side, so that will get multiplied by, we're looking from the base side, so we get multiplied by this factor beta plus 1. Now, we have the other expressions, that is VB2 by VB1, that is the gain expression for the common collector. And that remains same as before because there is no change here. So that will be RE in parallel with R pi 2, and that divided by RE in parallel R pi 2 plus we have RE1. Here is the common collector, and the last one VB1 by VS is same as this RI plus RS. So what change we are having here in this case? We compare with your previous situation. One change we are having in the gain expression for the common emitter, right? Instead of RL, we are having RI3. The input resistance of Q3 is working like this one. And we have this additional term that we didn't have, right? The gain of the common collector. So this is here is less than 1, we can say, because we are assuming RL is low, very low, about few ohms, so it will be much smaller than 1. But if you look at this expression for the common collector, there's a big improvement, because before it was minus GMRL, right? And now we have minus GM this RI3, right? And this RI3 is much larger than RL. So that is the main improvement, because before we have seen that if RL is 10 ohm, then overall gain reduces to only 0.4, right? Now, we have, with this modified circuit, RL gets multiplied by beta plus 1. So if beta is 100, right? So now RL, this RI3 will be almost, it gets multiplied by 10 or 100 and 100 times greater. So the gain will be also almost 100 times greater or more. So if you multiply by 100, so you get 40, right? 40 volt. So we can improve the gain almost 100 times by adding this. But again, there will be some loss here. Maybe let's say this is 1/3, then you don't get to 40, you get 1/3 of 40. So 40 times you do multiply 1/3. So something like 13 or something, right? So something like that. So it's still from 0.4 you can improve to, right, a much bigger number. Any question, guys?
No, sir.
So got the idea how we can improve the gain, how we can minimize the loss at the input side and the output side, right? Because common emitter has a low input resistance. So that we can overcome by adding a common collector at the input side and minimize the loss of signal at the input side, improve RI, improve gain. And at the output side, if your load resistance is low, then that will affect the gain, overall gain. And so that you can overcome by adding another common collector at the output side, right? And that will restore, right, part of the gain. Now, maybe this is not good enough, right? Still, right, 10, 20 may not be good enough overall gain. So if you want to improve the gain further, I mean, what you can do? See, the gain expression here is determined by the value of Ri3, right? Value of Ri3 is now the load resistance for Q2. Now, if you can improve this value, Ri3, then we can improve the gain. Is it possible to improve it further? Is there any way?
Sir, improve means increasing.
Yeah, yeah, not decreasing.
We can add a high resistance transistor which has a high input resistance.
Adding resistor doesn't help, because I mean, it will absorb most of the voltages, right? Whatever gain you get, that resistance will absorb. The load will not get that benefit, right? The voltage at the load will not change. It will not improve, right? Because the resistance will consume. Right? So unnecessarily will be increasing the loss in the circuit. So what I have done here,
Another common collector.
right? I have added another common collector. And now we have two common collectors in series. So what will be Ri3 now? Now, instead of here we had RL before RL was connected at the emitter of Q3. Now we have the Q4 connected, right? So looking into the base of Q4, the resistance is Ri4, right? So the Ri3 instead of RL, here will not have RL, rather we'll have here, what will have?
Ri4.
Right, we'll have Ri4. Right. And which will be, so this combination will be much larger sorry, Ri, much greater than Ri4, and okay, I think this color. The Ri4 will be R54 plus beta 4 plus 1 times RL. Right? And that is again much larger than RL, right? Because RL is getting multiplied by beta plus 1, so that is Ri4 much greater than RL. Ri is 3 is much larger than R2, so much larger than RL. So you get a, the Ri3 now will be substantially, right, larger than RL. Right? So overall, this Ri3 we can write as R pi 3. We have beta 3 plus 1, Ri4, sorry, Ri4, okay, yeah, Ri4 and R pi 3 plus beta 3 plus 1, Ri4 is R pi 4 plus beta 4 plus 1, RL. So we can ignore this one, right? This is much smaller compared to this. This is a very big number. So this one we can approximate to beta 3 plus 1 R pi 4 plus we have beta 3 plus, why not like this? Okay. So beta 3 plus 1 times beta 4 plus 1 RL. So that will be our overall gain. Sorry, overall the Ri3, the expression for Ri3. Now you see that, okay, but just trying to give an approximate the idea, right? So the idea of the approximate gain that we can have. So here, first of all, this part will be not that big compared to. So let's focus on this part. So this will only add to this and make the gain even greater. So, but let's focus on this part and see how much increase we can have in the gain. So let's say for both beta 3 and beta 4, for our sake of convenience, so let's say both are 100, right? So an approximate value will be, right? So this is 100 square RL, right? We're taking approximate and not the exact. The exact will be even greater. So we get 10,000 RL. So if RL is 10 ohm, so we get 100,000 ohm. So that means 100K. Right? And that if you add this one, you get 100K or 200K also here, right? So it will be much larger than this. Let's say the overall is 200K. Right? So now Ri3, well, the load was 10, right? Now we have enhanced it to 200K, right? A big number, right? And the overall gain will be minus GM. That was GM was 40, right? The 40, and that times 200. How much is it? 8,000, right? Is that clear, guys?
Yes, sir.
So this from in the last example where we had only one common collector, now we have two common collectors in series, and we are able to increase the from that was we found only 13 or 10, 20, so to the range of thousands, right? We can improve the gain, very high gain. Right? Is it possible to fix the gain, or how we can fix the gain? If you add a resistance here, let's say you add a resistance RC, right? You add a resistance RC, and then you have this Ri here, Ri3. So how the gain will modify for the common emitter part? How the gain expression will modify? That is our gain expression for this common emitter that was before adding this RC. Now we have added RC. So how it will change?
So RC will become parallel with this combination, R0 to RH.
So exactly, RC will come in parallel. So we'll have what will have Ri3 that will come in parallel with RC. So if we have this now, so how does it affect, right? How does it influence the gain of this common emitter? How it will influence the gain? Any idea? Can you figure it out?
Will be equivalent to minus GM to RC.
What?
So minus GM to RC, will it be equivalent to minus GM to RC? Because Ri3 is much greater.
Yeah, exactly. So this is R02 and Ri3, both are large, right? In the range of hundreds kilo ohms. So both will be, let's say, much larger than RC. So this parallel combination we can approximate to RC, and the gain expression will be reduced to minus GM to RC. So now the gain of the common the emitter, this gain of this common emitter will not depend on Ri3, and which actually depends on RL, the load resistance, right? So now the gain, common emitter gain will be independent of the load resistance. It will not be affected by the value of the load resistance. It can be It can be low, it can be high, right? But that will not affect the gain, because gain is now fixed by this our resistance RC, right? RC and GM. So both of which we can fix, and we can fix the gain. Is it clear?
Yes, sir.
So now your task is to analyze this circuit, the overall this three stage or four stage this cascade amplifier, and find out the different parameters of this circuit. Input resistance is already known, input side doesn't change. You need to find the output resistance, which will be different now because we have two common collectors on the output side. You need to find output resistance. You need to find the voltage gain, overall voltage gain, what will be the overall voltage gain, and what will be the overall current gain. So we did this analysis for the other circuits. So just apply those techniques, right, and determine these different the expressions for these different parameters. So that will be a practice for you, and preparation for your midterm that is coming up. Any question, guys?
Sir, now the gain is not dependent or on Ri3. So what if we remove Q4? Will it be possible?
What? What if?
What if we remove Q4?
Oh, remove Q4, then you get low value for Ri3. Ri3 that we so showed in the previous calculation. Ri3 will be 1K, right?
Yes, sir.
About 1K. So if you are taking RC, let's say 10K to have a high gain, and now in the overall resistance will be reduced to only 1K or less than that, right? So that will
Okay.
reduce your gain, right? It will depend on,
Yes, sir. Then
it will affect, right? RL will affect the gain, right? So we have added the two common collectors, so we can substantially large resistance here. And so the overall, the resistance, load resistance at Q2 will be mostly determined by RC, not Ri3. If Ri3 is small, then it will affect. But if it is very high, it will not affect. So that was the main idea, to have these two common collectors at the output side to make it very large. So it doesn't affect the overall gain. Overall gain is determined mostly by the RC.
yes. Okay.
Guys,
Sir,
any question?
sir, when will be our midterm?
We're planning to take it on the on, in the midterm week on Thursday, uh, most likely in the evening.
Okay, so by 26th.
Yeah, yeah, 26th. Yeah,
Okay, sir.
26th.
Sir, any quizzes before that?
Hmm?
Any quizzes?
No quizzes.
Okay, sir.
We'll give you some homework assignment for you to prepare and practice. Okay.